Hi, I'm Gary Sieling. I'm a principal software engineer at Pinnacle 21, a recent acquisition of Certara, where I work on shaping and building new software products in life sciences. And I'm currently a product lead for a cloud data science platform. I'm going to talk in this talk about metaprogramming in R, which is the ability of developers using the language to change its behavior at runtime. R is a functional programming language in the same vein as Lisp languages. Specifically, R lets you treat code as data that the language can operate on. The language is about 20 years old, and it's based on a commercial statistics programming language that was called S. And so you can see where the name comes from, first S and then R. R is an interpreted language, and it allows you to access some of the interpreter's data structures at runtime, such as the abstract syntax tree and portions of the call stack. If you're not familiar with what an abstract syntax tree is, that's the data structure that represents the code that you're running after it's parsed by the interpreter, and I'll show some examples later in the talk. The language is run through the Free Software Foundation, and the governing body is composed of math professors. Because of this background, there's some decisions in the language ecosystem which are unusual relative to a lot of languages that software developers are accustomed to. And so, for instance, there's a lot of documentation that you'll find in PDFs. And while that's not necessarily the case for all of what you'll find, it's an interesting look into the window of what kinds of file formats people are accustomed to working with. In a similar vein, many of the basic data structures are a little different from typical languages used in most software engineering. For instance, rather than primitives, all the operations that you work with happen on vectors. A lot of operations are also done with data frames, which are a common tabular format now in a number of data science languages. And to support programmers that do math, the language offers a lot of syntactic sugar that allows you to use syntax resembling what you'd see in a paper. And so I'll work through a series of examples here and build up to something that shows some of the power of metaprogramming. So as a brief first example, we'll take and make two vectors, x and y. And while these look like primitives, when we ask the language to print them back, they print out as if they're a one-dimensional vector. You can see here as well that the assignment operator, this arrow function, is the same as an equality assignment operator in other languages, but of course looks a little bit different. And it looks a lot more like something you'd see in math. We can, as you would expect, add these two things together. But just to prove to ourselves that these really are vectors, I'll define x and y again as two-dimensional vectors instead of one. And you can see that the output looks the same. If we do x plus y, we get pairwise addition of the elements in the vectors. So I'm going to show a syntax that is unusual and specific to R now. So we'll redefine x back to 1 just for simplicity. We'll define a function that is the identity function. And you'll notice here in this syntax, if you've used other languages like Scala, that R is returning the last statement in the expression as the output of the function. So if we do f of x, we get 1 back. So now let's try something new. Let's try assigning the output of f of x to be 5. And we don't expect this to work because in most languages this is not possible. And as expected, we get an error, but the error is not what we're expecting. It says, instead of saying you can't do this isn't valid syntax, it says error in f of x takes 5, can't find function f assign. And this is kind of an interesting error because you wouldn't expect a function syntactically to look like this. And in fact, R allows you to create a function like this, even though you can't directly call it in the way that you might expect. So let's do that. By putting a string in backticks, we can create a function with this name. We've made a function here that takes two arguments, temp and value, and it assigns the value, which is the second parameter, into temp. And so now if we do f of x takes 5, it succeeds. And if we print X out, we get 5. And so what's happened here is R has allowed us to change the behavior of the assignment operator in a useful and interesting way that allows you to write syntax that looks a lot like something you might see in an actual mathematical paper. Another major feature of the language is the charting ecosystem. And I'm going to show an example here of how you might build up a chart, and this will show us some other things that are important when it comes to learning how metaprogramming works. So first I'll import some libraries, and then I will create a data frame. And a data frame is just a tabular data set. We're going to have 2 columns, name and value, where name is just a static string and value is a randomly generated item. We have some nice integration with the IDE where we can type in this view function and pass it the data frame, and we can see what our data frame looks like. And so you can see this is just a table. We can then take that data frame and make a chart based on it. So I'll make the chart and then talk a little bit about a couple of interesting pieces of syntax here. So if you see over here on the right, there's a box plot that's generated from this chart. And already this is more sophisticated than charting packages in some other languages because it's clear, and you can see that it's clearly made for people who are doing some sort of statistical analysis. If we look at the syntax that we're using here, we're taking the data frame that we defined, and we're using a special operator that pipes the data frame into this larger expression that generates a chart. So this whole thing here produces the structure of a chart. It takes as input the data frame. And you'll notice that this operator is pretty special. I don't think I've ever seen this in any other language. There's about close to 30 operators in R at the moment, and you can change the behavior of them to make new and interesting features. I want to highlight a couple of interesting pieces of syntax in the code that generates this chart. The charting code is using a library called ggplot2, which defines what it terms a grammar of charts. And the cool thing about this is that if you're a person who wants to build a chart, you could use the charting features that are given to you, but you could also say, I don't like the way it renders points, or I don't like the way it renders the axes. And you could write your own library that does something new and sophisticated and generates something entirely different than what's there. And so there's a lot of libraries that you could mix and match to get different chart outputs from. And in this, we can see, for instance, this line, which defines how the points are rendered. And this takes named arguments instead of relying on their order. So it's taking color equals black, size equals 0.4, and alpha, or the transparency, is 0.9. And this isn't something that's unique to R specifically, but not every language has this, so it's kind of a nice feature. But if we look higher in this, where the code defines how the plots are located, meaning the X and Y axis, we see something kind of unusual here. So X equals name, Y equals value, that makes sense, right? Those are columns in our chart. But what's interesting here is that the way that this syntax looks, name appears as if something that we're closing over in the external environment. We know that it isn't because we defined this data frame and we didn't get an error, the thing worked, but we don't have to define these as strings, and R knows what to do. And this is a part of a feature known as shadowing. So I'm going to build up an example that shows how you can build things that use shadowing. I'll show some issues with it and some challenges. But this is a really neat feature of the language that has a ton of power that you can use. And before I build the shadowing example, I'm going to show a couple more pieces of important syntax because there's some assumptions built into the way the interpreter runs your code that you need to know before you can make good use of this. So first, let's just print out a message. This is kind of a classic hello world thing. We print out a warning. You would use this function for logging. And then we'll define 2 functions, one called identity and one called ignore. So if we pass to the identity function the warning, we get exactly what we'd expect. it prints out the message that we passed in. So no surprises here. Now, if we take the second function, which is called ignore, and we pass warning, we get no message back. And the reason that this is happening is that the arguments that are passed to the function are evaluated lazily. So because this expression is never referenced inside the function, the argument's never used, it never gets evaluated. So if it was something that generated errors or didn't work, it would actually just never get run. But there's more happening here than just lazily evaluating this function. And to show why, I'm going to generate a third function, which I'm going to just call args. And so what args is going to do is it's going to take and it's going to print out the output of this second function called enquo, which is taking the arguments and creating something which R calls a quosure. So let's take this function and we'll pass warning hi. And what we get back is really interesting because instead of having the function warning or the value that is its output, we actually get the expression back that we passed in. So as the consumer of the function, we see not only a value or something that's passed into us, but we actually see the code that was used to generate the promise that we're evaluating. And we see the environment in which it's evaluated. And to maybe make this clear, let's call args of x plus y. So we get the same thing back. We get x plus y, and we get an environment, which is called global. And what this is saying is that when this code is run, it's going to look for x and y in the context of my REPL. And as we know, x plus y exists. Outside of the function, we can get this object in a more direct way by calling expert. This is just going to give us back the abstract syntax tree. It doesn't look like very much because it's just printing out what we passed in. So if we'd like to see a more interesting example, we can render the AST in a way that shows the data structure that sits behind it. So we're going to take f of x plus y, and we see here now that we actually have a tree. F is at the top, which makes sense. F is the function we're calling. It takes as an argument a second tree, which is plus. So plus is the second function, and plus is taking x and y as its arguments. So x and y are passed to the plus function. It evaluates. The output of that is then passed to f. And that matches what we expect. And you can see that these are ASTs in another way. If we were to take the expert function and we were to just put a bunch of extra white space in here, what we see is that what it prints out is always going to be the same thing, no matter the structure of this input. Because all of these things are really evaluating to the exact same thing. The white space is irrelevant. It's always x plus y. So what we're really seeing is that R is taking our code that we give it, x plus y, it's parsing it, and then it's doing a toString on the parsed output. So anything that resolves to the same tree is going to render the same way in our shell. And if we want to take one of these ASTs, we can reverse one of them by calling eval. Eval of x for x plus y is the same thing as if I had just done x plus y in my session. So it's worth thinking now about what is the difference between a function that takes two arguments and returns an expression that we evaluate and the expression itself. And I think it's pretty obvious, right? X and y here obviously coming from the arguments of the function. So we know exactly where x and y come from. And if we defined a different function where we said f of x and we return x plus y, in other languages, we would call that closing over a value. We expect y to be defined outside of the function. It's very apparent to the developer that you're relying on something that's been defined outside. In JavaScript, that's something that gets carried forward with a function kind of in a way. So if you're a JavaScript developer, this is probably even a kind of a familiar concept. And so we can think about what the environment means in R in a different way than something like JavaScript because the interpreter itself allows us to have a lot more access to this particular data structure than other languages do. So let's imagine now we'll think about this by using some variables that we know don't exist, like a and b. So if we took expression of a and b, what's interesting here is that these are things which don't exist. We can still reference them in our code because this code isn't being evaluated. So this expression really exists separate from the environment in a way that a function doesn't. So just to take an example, so that we can think about how closing over a value works in more detail, let's set y back to 1, and we'll actually define the function I described before that takes x and it adds it to the y that's in the global environment. And if we do f of 10, we get 11, just as we'd expect, because we know y is defined, 10 plus 1 is 11. We can ask R to tell us what the environment for the function is. And here you see it says the global environment, and this means that f is defined in the space of my REPL. We can also make a new environment, so we'll do that. We'll make a variable called e, we'll make a new environment, and then we'll use the left-hand side assignment concept that we learned earlier in the talk to assign e to be the environment that our function operates in. Now let's try doing f of 10 again. We still get 11, and the reason that this works is that e has a parent environment, which is the global environment. Because I made it from my environment, it automatically inherits the place that it was made. And we can see that by doing parent.end e, and you'll see that it returns the global variable. So when we ask e, what's the value of y, it says, I don't know, I'll check my parent, and it passes that request up. So we could define the variable y in e. We could do ls of e, and we'll see that y is now in there. And if we do f of 10, we get 17 now because e knows a new value for y, and it shadows the value that's stored in our global environment. And just for the sake of completeness, now that we're all done with this example, we can remove a variable from an environment by doing rm. You'll notice if you're familiar with shell commands in something like bash, this is these functions. Some of these function names are clearly borrowed from there. And so now if we do f of 10 again, we're back to 11, just as we started. So it's worth returning now to the original example that I had, where we do make a function named f_assign and give it a definition. And what we're doing here is we are taking and making a string token that contains this value. We are assigning its value to be this function that I'm defining here. So the environment, in effect, is a map or a hash map that has tokens as values, and as the values in the map are expressions in the R language. And so you might ask yourself at this point, what other things can I override? Because if we can override things which aren't natural syntax, there's probably a bunch of other neat things that you can do in R. And we can look at some things which are already defined, such as a parenthesis. And so what this is representing here is a function that is taking something and returning what you pass it, just the same as the identity function. So if I do 1 plus 2 this way, it's the same as if I had typed 1 plus 2. And there's an alternative way to call functions that are written this way. So we can take and ask R to find the function and call it with these values. So if we do this, it's the same exact thing as if we had done any of the other alternative syntaxes to get this result. And just to convince you even further that this is a realized thing, this parenthesis function, we're going to do a timing of 2 different ways of adding numbers together. So here we have 2 different expressions, 1 plus 2 plus 3 and 1 plus parenthesis 2 plus 3. In most languages, these are exactly the same things. The compiler will realize that the parenthesis means nothing here, and these would be the same. But in R, these are actually different. You'll see that the min and max times and the medians are higher for the second expression. So you have to think a little bit sometimes about how you write your code, because sometimes things have an impact that you don't expect. And there's really two things happening here that make this take some time. First, R has to look in an environment to find the function, to figure out what to do. And then if there are a sequence of environments, like the environment doesn't have it and there's a parent environment, it has to go look higher up. So if you imagine a situation where instead of having one environment that references the second one, if you had 10 or 100 or 1,000 layers of environments, like you might have in like a call stack, R may potentially have to look a fairly long ways up the tree to find things that you're looking for. And so in some cases, doing something with performance tuning, this may be an area where you want to think about how you write your code. If you have a lot of environments and R has to do a lot of lookups to find stuff over and over and over again, it's going to take some potentially noticeable time. So just for the sake of exploring this a little further, let's try overloading the behavior of this operator. And we're going to define a function which takes a value and doubles it. So now if I do 1 plus 2, we get 6. So you can obviously do things which you probably don't want to do. So let's try, as an additional example to understand the language, let's try changing the number of arguments that this operator takes. You might expect that if this operator could only ever take one value, that you'll get an error when you do this line. I'm going to take and double both of the arguments and add them together. But in fact, it works. So the question here is, have we changed the behavior of the parenthesis function, or have we broke something? Let's try doing this. So this doesn't work. R doesn't expect it. Let's just try doing that. And you see now it doesn't know what to fill in for Y. So we have attempted to change the behavior of this operator, but we actually can't do that. And R doesn't know what to do with it now. So you've completely broken our REPL. And the thing that's important to identify here is that R is doing its checks at the last possible point. Similar to arguments to functions being promises, this whole thing is doing the least amount of work up front as possible, which is common in a lot of functional programming languages. So before I continue, I'm going to undo my overload of this operator so that I can get my REPL back. And now we're going to work up to a shadowing example. So if you remember the original data frame that we used, we have a name and a value. And it'd be nice to be able to do something to filter this data frame. And we can filter it by using this operator with a quoted string. And this gets us back the first column. We can do the same thing to get the second column. What I'd really like to be able to do is a syntax like this, where I do data frame, bracket, value is greater than 10. And that would give us all of the rows where value is greater than 10. So in concept, what we might imagine doing is doing something where we take that operator, we overload it with a function that filters using the expression that we've provided. I'm not going to do that in this talk because it's really easy to break the whole system. A lot of things rely on this operator. But in concept, what we can do instead is to define a function that we're going to call filter. And for our first version of this function, we're going to take a data frame and an expression. We're just going to print out the expression or the closure that represents the expression to make sure we're getting what we expect. So let's call filter, data frame, and value is greater than 10. And what you see that we get back here is exactly what we'd expect. We get an expression that says value is greater than 10. Value obviously doesn't exist in my global environment, but this expression is tied to the global environment. And so there's our first problem. We don't want anything tied to the global environment. We don't care about that environment now. So instead, we're going to use a second function, which is nexpr, and that will return us just the expression that we passed in. So that's a lot closer to what we want. And to make this work for real, as I showed before, we're going to want to make a new environment. We're going to want to loop over all of the rows in the data frame. We're going to want to loop over each column. And then for each cell, we're going to find the name of the column we're looking at. And we're going to assign into the environment the column name and the value of the cell at that point. So after an iteration through this loop, the environment is going to have two variables, name and value. Name is going to be the name from the name column of the row that we're looking at, and value is going to be the value from the row that we're looking at. So having done that, the next step that we're going to want to take is to evaluate that query that the user has given us in the context of this environment that we've made up. And for the sake of argument here, what we're going to do is we're just going to print out if there's a match. So to demonstrate this, I will take this and run it. And we get the result we expect. We get a bunch of rows from our data frame where all of the values are higher than 10. But there are some defects in this implementation. Let's first talk about changing how we call the function. I'm going to define a variable called threshold, and I want to pass that variable in to our expression so that we can change it from the outside. It still works, as we'd expect, but from the standpoint of reviewing or understanding someone else's code, this is actually pretty awful. If you look here, we have a value variable that's defined inside of our data frame and a threshold variable that's defined in the scope of the REPL. And it's really confusing to look at. And I think if someone was looking at this in a code review or something, this is something that people would really struggle to understand what's happening here. So we want to prevent this from happening. So one solution that we can take is we can take the original function that we wrote and we can make the parent environment for our made up environment be something called the empty environment. And so what that will do is it will break the lookup so that when threshold is looked up, it shouldn't find it. And so what we expect now when we call this filter function is we expect to get an error that says threshold isn't defined because in our environment that we've made up doesn't have a parent, threshold isn't in the environment we've made up. So it should work. We should get an error for using threshold, but value should work. And in fact, this almost works, but it doesn't fail in the way we expect. It now can't find the function that represents greater than, which is a little bit inconvenient. So our empty environment is really empty. And there's a few different ways that you can fix this. And I'm going to show you a way which isn't the right way, that's a little more difficult, but which shows something about the way the language behaves that's really important to understand metaprogramming fully. When we call the filter function, one way that we could represent this is using the alternative syntax where you find the function greater than and you call it with two values, right? This is something that we know we can do. It's kind of unintuitive syntax for most people, but this does work, and this is something that's very Lisp-like. I'm going to insert an operator here, which is called a splice operator. And what this will do is it will tell the command line to, instead of putting the token greater than in the AST, it's going to look up the function in my current environment, and it's going to put the function in the AST. And so when the filter function receives this expression, it's received the correct function, and then the two tokens, value and threshold, and it has to look up value and threshold. And so here we get the error we were originally expecting, which is that threshold is not found, because threshold isn't found in that environment. And we don't want to do it this way, though. It's not a great experience for the end user. So as it turns out, there is an R package called base, which defines a lot of language features. And if we scroll down to the bottom here, we can see that operators are included in this list, including the greater than operator. The package has its own environment that comes with it, so we which allows you to do things like reference the original function if someone has made two functions with the same name. If you import a library and it makes a new function that kind of shadows something you already had, you can always get back to the original one using this namespacing syntax. And so what we're going to do is to import the rlang library, which gives us a function we can use to find the environment for this package. And in our filter function, what we'll do is we'll define our environment as a child of the base package. So it should have everything that's in base and nothing else, which includes the greater than function. Now, this may not be the way that you would really want to do this for real, but it's a good demonstration to understand what's possible. So now let's do filter data frame value greater than threshold, and we get the error we were expecting. So that's great. We have access to value, we have access to arithmetic function things, but nothing else. And the person who's doing this can't pass threshold in this way. So I'm going to move on and show another potential issue with this. Let's say if instead of defining threshold as a variable, we define it as a function. So let's define threshold to be function, doesn't take any arguments, it just returns a 10. Now, this looks like kind of a silly thing to do, right? It's just returning a static value. But in a real system, this is a kind of thing that can actually happen. Someone might write a database query, or they might write a REST API call that goes and looks up the threshold. Maybe it's a setting in some system somewhere else, and we want to look it up. So the person who's doing this might then use threshold in this way. We pass in the expression value greater than threshold, the function. And the problem here is that the person who does this is telling our filter function for every row in the data frame, you need to evaluate this whole expression, which means this is going to get called every single time. So if you do something and it takes, a couple seconds or even tens or hundreds of milliseconds, it's going to be really slow to do this filter function. And so to demonstrate another capability of the language, what I'm going to do is I'm going to say, let's say for the sake of argument, we want to fix this as the recipient. Inside of our filter function, we want to detect that someone did something that they shouldn't do, and we want to replace this threshold with its value, which is 10. And this shows another side to the power of metaprogramming. This behavior that we're doing is called memoization. So this is essentially just calling a function and caching the output. And to show you how we might go about implementing this, I'm going to first take the expression that we want to use as our test expression, and I'm going to stick it into an object that represents the AST, just so we have something that we can work with. And so you can see that Q is our expression. R gives us some capabilities that we can use to look at the AST in different ways. So for instance, we can ask if it's a function call. Now, why, you might ask, is this a function call? Obviously, it looks like one, but let's print out the AST so we can make sure we really understand the structure. So the function call is actually the function call to the greater than sign operator. It takes value as the first argument, and then it nests. In the nested option, it's then a call to the threshold function. So this is a little different than some of the things we've looked at before. We have the ability to access our AST as if it was an array. And notice here that this is a one-based indexing system. This is a unique characteristic of R. So we can do 1, we can do 2, and we can do 3. And we see here, we get the greater than sign for the first thing, the value for the second, and then the call to threshold for the third thing. So this makes a lot of sense. And we can do on each of these tests to see what these look like and see if they're something that we want to use. So let's do is.call of the first item. It's dot. So what's happening here is kind of interesting because the greater than sign looks like a call, but what it actually is it's just the token that's the name of the function that's being called. The second one, we don't expect to be a call because it's just a reference to a variable. And then the third one is a call, and this is how we know that there's something that nests in the tree structure. And so this test is the first piece of what we need to be able to detect a function that needs to be memoized. We know that the third item is returning true, and so we want to check for that. But there's some other checks we can do to make this safer. There's a second option, which is symbol, and we'll call that on all three of these. And we'll see that it's true for the first two and false for the third. And this also shows us that the function is nesting in the tree. And we really want to look at that nesting concept. The third thing we can do is we can take the item that we're looking at and we can ask it if it's defined in an environment that we've made or if it's defined in the parent environment. And to do this, what we actually need to do is to add to Q3 a second level of nesting. So it's really as if we have two layers of arrays, and that gives us the token threshold. So in our filter function, we would look at the parent of the environment that we've made up, and we would ask if threshold exists in that. And if it does, that's a pretty good sign that somebody's calling the same function over and over again. So if we combine all three of these things together, we get a condition that we could use to detect something that we want to memorize. Now, this may not be the perfect condition, but it's good enough for our demo purposes. And what we want to do is we want to take that third item in our query, and we want to replace it with the eval equivalent. So if I do this, Q now is value is greater than 10 instead of value is greater than threshold. So I will set this back to what it was so we can do another test. In a real application, if you were going to work on an abstract syntax tree, you would write code that uses recursion because this could nest pretty deeply. But for the sake of writing something for a talk, I'm just going to treat this as like a two-level array, and we're going to map over the top level. And in our example, what we're going to do is we're going to map over all the items at the top level of the tree. And for each item, we're going to check this condition that we've built up. If it matches, we're going to return the eval version of the expression. Otherwise, we'll just return the expression. And what we get back is essentially what we asked for. It renders a little differently, so we would probably want to work on fixing the data structure to make sure it's still an AST. But in essence, you can see that what we've done is to replace our original expression that has a function call in it with a new expression that has a value in it. And ultimately, this highlights a lot of the value and the power of the R programming language. You can use the language to take code that you're given and to do something like detect a call to a slow operation. An example where you might want to do this, there are a bunch of different JSON parsing libraries in the R ecosystem. Originally, one of them was slow, so someone wrote a new one that was faster, that was implemented in C, and then some of those changes got backported. But ultimately, over time, there are a bunch of different versions of a bunch of different libraries. Some of them are faster or slower than others. So you could detect that someone was using a slower library. You could replace it for them without them even noticing. If you had some code that you had to interact with that was written by a scientist that you weren't allowed to change, you could potentially go and fix it after the fact without doing anything that actually touches the code. Another example that you could do is to be given a piece of code and you could do some checks to look for potential security implications. Kind of like a linter, but something that runs at runtime that removes calls which are potentially dangerous. Or you could look for things which are calls to external APIs and you could replace them. Another thing that you can do is you can construct expressions at runtime. You could build functions at runtime. So if you had access to information about the shape of someone's API, you could build functions that allowed you to call that API at runtime while your code was running. An example here is, say you use something like OpenAPI, which gives you a schema for an API. You could look through that. You could build the functions at runtime and allow someone to have code that they can use against an external system. Some of the libraries that are used for things like benchmarking and tuning and memory will use this capability of the language to kind of insert themselves as calls into other functions. So there's a ton of power that you could use here. And I kind of got down this road by looking at how I would tune an R program and realize that there's a lot of capabilities that the language offers you that allow you to change its behavior. So you don't have to worry as much about issues in the runtime if you can fix them outside of the code base that you're looking at. So while R is definitively a domain-specific language that's geared towards statisticians, if you're a software developer, at first glance, that may not seem quite as interesting, but I think you can see from this that there's a lot of really interesting computer science concepts buried in the language. If you are someone who's looking to learn R better, but you don't necessarily have the mathematical background or you want a useful path to explore, one thing that's really great about the community is that there are a lot of people who will write libraries or papers on specific data sets, and then they do a lot of really interesting mathematical analyses, and so you can find a paper and follow along with it. A really great example of that is papers that look at data from smart fitness watches. So you can do things like look at your own history of running or bicycling or something and follow along with a paper written by someone who's a real mathematician or a biologist or something, and do some analysis that maybe would otherwise be inaccessible to you. The other thing that you can look at if you like this topic specifically is there's a really great book online called Advanced R, which has a ton more examples like this. And if you follow through them, you can find lots of great detail. And if you were going to write a real library that used this, I would highly recommend going through that. All right, so that's it for my talk. Feel free to reach out if you have any questions. Thank you.